Hey, it's your favorite science teacher. This is Mr. Pugely. I want to say good afternoon. I hope you're doing well. What we are doing is this is our asynchronous day assignment. We are learning about ionic compounds, and we're going to combine all the stuff we've been learning and using this right here, right now. So, what I need you to do is you need to have out some of your materials for this. This is one right here. Some of the others include, right here, your periodic table that has the valence electrons and that, and you also need your your practice ionic compound sheet, and you also need your bell ringer for 1021 out. So that's what we're going to do. So what we're going to do for starters, let's go ahead and start. I'm going to share my screen. Right. Okay. All right. And so what we're learning again right here is we're going to learn how to draw Lewis structures for various elements. We're going to identify the most common ion and the common ion and valence electron for each element, and that's also called oxidation number. We're going to draw the Lewis dot structures for various ionic compounds before and after. We're going to explain what electron affinity is. We're going to identify and explain what it means to have high electron affinity and low electron affinity. And we're going to identify and describe the properties of ionic compounds and identify what a chemical bond is and why they form. All right, I'll pause it for just a second. All right, and so I'm back. I wanted to add a couple of questions that kind of helps us think about why this is important. First off, what are ionic compounds? What's some example of some ionic compounds? Why do atoms bond? Why don't they just stay separate? Why do atoms come together? Right? Who cares about electron affinity? What's the big deal about that? And so those are some of the things that we're going to learn about here today and with our lesson here. And so with that said, I just wanted to mention those things right here. So I'm going to start with the bell ringer. Okay. We'll start with our bell ringer. And it says, if you have an affinity to something, what does that mean? Right? You should have said, if you have an affinity to something, that means you have a natural attraction to it. All right. You have a natural attraction, affinity, just drawn to it. Right. And so if you have electron affinity, which we're going to learn about today, that means you have a natural drawing to the electron. It's just natural. It just happens. And it's just, it's not forced or anything like that. It's an affinity towards that. Next one, what does the word stable mean? Right? The word stable means, it means set, doesn't want to change, not reactive. If something is stable, it's set. It does not want to react. Um, it doesn't rely on something that's stable, it's set. It doesn't need to change. So again, I would compare the word stable and unstable as this. I like to think about this. About 8 years ago, my family moved to our house in Prattville. And when we moved that day, we moved over the weekend, and um, we found it. We had to go to school on Monday, and we didn't really prepare the night before too well. And so when we got up in the next morning, stuff are still not where it was supposed to be. And so we were like, "Oh my gosh, where's this? Where's this?" We had to leave, and had to be on places in time, but we weren't unpacked and ready to go. So at that moment, you'd say we were stable or unstable? We were unstable. And so we were actually kind of frustrated and reactive. And so We kind of say that. So we were not set at that moment. We did not want, we wanted to change. And so at that moment, we were unstable, not set, all right, wanting to change. And so it kind of gives the idea, a contrast with the word stable. We're going to talk about how atoms are stable or unstable and why they are like that. What is a chemical bond? Right. I read a lot of your papers the other day and I saw what chemical bond is, but a lot of times you didn't say really what it is. A chemical bond is a force that holds atoms together. Okay, it's a force that holds atoms together. Why do most atoms try to bond together? Why don't they stay separate? Um, Again, we're going to see today that atoms bond together because it's actually energetically favorable. Okay, atoms being separate is not favorable. Nature wants to do the easiest thing. And so one of the things that atoms will do is they'll come together and bond and chemically bond. And so that's what they'll do with this here. Overall, in cars, does the use of gasoline release a lot of energy or absorb a lot of energy?
Okay, Kenny Fernandez to the front office for early dismissal. Kenny Fernandez.
All right, and so gasoline releases a lot of energy. It releases a lot of energy. You have to give a little energy to start it, but then it releases a tremendous amount of energy. That's why we use gasoline all the time for our power our cars, because they release a tremendous amount of energy. Well, we're going to see that some elements are going to release energy. They're going to be exothermic when they gain electrons. And then there's some that do not want to gain electrons, so you have to force them and you have to add energy. They're going to have to be like endothermic here or endergonic. Um, the last one here, and so is in chemical reactions atoms will gain or lose what, but they will never gain or lose what. So atoms will gain and lose electrons and share electrons, but they will never gain and lose protons and neutrons. That's not what they do in chemical reactions. All right, and so what we're going to do is we're going to start over here, and we're going to um, talk about right here. All right, and again, write down notes on your sheet. All right, you're going to write down notes on your sheet here. So what I mean by the sheet, write it on your margins here. Okay, like I gave you all these margins. All right, so all those margins right over here, I need you to write down notes for that. Okay. All right. So going back. All right. And it says a bond is typically a mutual attraction or a force between the nuclei and valence electrons of different atoms that binds them together, that holds them together. It's a force that holds them together. Can be formed by gaining, losing, or sharing electrons. Why do atoms form bonds? All right, and I like this picture. I've been using this picture for a while. If you look at this picture down here on the right, all right, if you look at it, this is two hydrogen atoms, okay, all right. What is being changed on purpose in this experiment, in this little demonstration, this little graph? Yeah, it's the internuclear distance, okay. What is being measured? The potential energy. All right, and so the potential energy is being measured. All right. Now, which requires more energy? Okay, which one requires the least energy? One, two, or three? Which one requires the least energy? And you'd say two, and that's where the atoms are held together and they're bonded together. Whereas the atoms that are separate actually requires more energy for them to be separate. And so atoms naturally want to, not all of them, but most of them want to bond together. And because that's lower energy. Okay. Most of them want to do that. That makes them more stable, set. They don't want to change. For most atoms, they typically want to bond, right? Too close is actually forceful here. So again, why do atoms form chemical bonds? So that they can have because it's the easiest. It's nature prefers that, and it's the lower energy. It requires less energy to form a chemical bond than for atoms to be separate. So again, it requires less energy for atoms to form a bond than to be separate. All right, so write that down there. All right. Um, all right, and so let me exit this here so that we can kind of get that last thing here. All right. It requires less energy atoms to bond together than to separate it, than to be separate in nature. And I would add most atoms, not all atoms. That's not the case for all atoms. And when we do chemical bonding, it's only the valence electrons that do this type of bonding. All right. All right. First type of bond is ionic bonds. Ionic bonds are caused by the losing or gaining of electrons to satisfy the octet. There are two types of ions. There's the anions and the cations. And another way of saying this is that they transfer electrons, okay? In ionic bonds, electrons are transferred between the two elements. All right, and so that's what they do right here. When atoms lose an electron, they become cations, and when they gain electrons, they become anions because they have negatively charged here. All right. Trends on the periodic table. These trends are almost help show why they do these type of bonding. Okay, they kind of show why they do the type of bonding that they do. Ionization energy. Ionization energy is the energy required to remove an electron from the outer shell. Electron affinity is the one that we really want to focus on here today. The change in energy when an electron is added to the outer shell. For bonding, high ionization energy, high electron affinity, it's less likely to give electrons. It's going to make an anion. Low ionization energy and low electron affinity is more likely to give electrons and make a cation. And so it says, need more convincing, we're going to draw the orbital diagram for fluorine. So let me pause for a second and we're going to do that real quick. All right, and so we're doing an orbital diagram for fluorine, and I'm going to show you my screen over here. All right, and so here is fluorine. All right. All right, so if we do orbital diagram for fluorine, we got the 1s orbital. Got one, that's filled. We got our 2s orbital. It's got one, it's got another that's filled. And then we got our 2p orbitals. And again, we have a total of 9 electrons if you look on for fluorine. So we've already done 4. So 1, 2, 3. All right, so I got 7, 8, 9. And those are all the p orbitals. Now, it is one short of that last one being full. All right. And these atoms are going to try to get what we call a noble gas electron configuration. They want that last electron, like these noble gases, and that makes them more stable. All right. In fact, this diagram that we're about to see right here, if you look, I'm going to make it a little bit bigger so you can see it really nicely here. All right. This is the electron affinity diagram. Means if you add an electron, what will that atom do? All right. And if this, a lot of them got these negative numbers. Okay. That when you add, that means it'll take the electron and it'll release energy. And that means it's kind of energetically favorable. All right. It kind of wants to do that. Okay. And so anytime you see a negative number, it's willing to take an electron and release energy. It's like it's energetically favorable. It doesn't mean you don't have to force it. All right. And if you look over here, here's fluorine. If you look at all the elements, these are about negative 72, negative 59. And you can see that the electron affinity decreases. All right. And so it releases, this will actually releases more energy as you go up. But if you look right here, fluorine really and chlorine really want electrons. They release a tremendous amount of energy when they gain an electron. And the reason for that, when they gain an electron, they get this orbital gas notation. This is energetically favorable. When they gain that electron, they get that orbital, that noble gas notation. And that's what they want. So that's the reason why they really want an electron. You can see that lithium and beryllium, they don't really care for an electron. None of the noble gases want one. In fact, you have to force it, you have to give it, add energy for it to gain an electron. These will not, if you give an electron, it will give off energy because it's natural. Remember, I was talking to you about gasoline. What does burning gas release energy, or does it absorb energy? What does it do overall? It releases energy. Well, these things release a tremendous amount of energy when they gain an electron. All right. You don't have to add energy. You're like, oh, come on, come on, come on. Yes. It's like when something you really want to happen. This is what they really want to happen. Helium and all the noble gases, they do not want an electron. So you have to add energy and make it happen and force it in order for it to happen. This is not natural. Helium does not naturally want that. So this is energetically favorable, okay, for it to gain an electron. And this is going to set up ideas for how chemical bonds will happen, all right? And so let's write something over here, all right? Okay, so the more negative, right, the more exothermic it is, and that means exothermic that it is right here. So let me write over here. Let's see here. Let me write in the thing here. Okay. The more right, the more negative, the more negative an element is, an element's electron affinity, an element's electron affinity means the more energy it releases. All right. And if you remember, the more energy it releases, all right. And if you remember, which one had high electron affinity? Uh, the halogens, group 17, fluorine, halogens have very high electron affinity. That means they release a tremendous amount of energy when they gain an electron. On the other hand, um, on the other hand, the noble gases have no electron affinity. You have to force them to take an electron. Noble gases have positive electron affinity. When you have positive, that means you have to force it. Noble gases have positive electron affinity. Must be forced. Must be forced to take an electron. All right, and this is really key because this is why atoms chemically bond. All right, this is why atoms are going to chemically bond, is because of this electron affinity, how much they want it. And atoms are typically trying to do is trying to get that noble gas configuration, their noble gas configuration for this here, for elements. All right, and so let me go back over here. And so the trends are the reason why an atom tends to gain or lose electrons. The number of valence electrons determines how many electrons are lost or gained. All right, and you can see that. I mean, we can see that on our table here. And so it determines how much they want to gain or lose electrons. All right, and so what we're going to do now is we're going to get this periodic table out. Okay. All right. And we get this periodic table out, we're going to see that we've kind of done this already, but we're gonna make it official right now. The number of valence electrons here. Group 1, which are the alkali metals. These are called the alkali metals. All right, that's group 1. They have 1 valence electron. Group 2, which are called the alkaline earth metals. They have 2 valence electrons. All right, group 13, which is 3A. It's 3 valence electrons, 4A, 4 valence electrons, 5A, 5, 6, 7, and 8 valence electrons. All right. The transition metals, their number of valence electrons can vary, and what their charges can vary. So that's group 3 through 12. Groups 3 through 12, which are called the transition metals. Their number of valence electrons varies. Okay. I forgot to say, I want to make sure we understand that group 18 or group 8A is called the noble gases. This group is called the noble gases. And this group right over here, this is called the halogens, that group 17. Okay. So that's all we have to draw right over here. And here's our noble gases. Oops. And no, that's noble gases. And this is the alkaline earth metals. And this is the alkali metals. All right, so we've gotten all that right here. And so we've done that. What we're going to do now is we're going to add oxidation number. Okay, oxidation number. Let's write the definition here. Oxidation number is the most common charge when an ion is formed for that atom. is the most common charge when an ion is formed for that atom or element. Okay. And for group one, remember they had that low ionization energy. And so they're not going to usually keep their electrons and they don't have that high of an electron affinity. So their oxidation number is they're going to typically have a +1. That means they will lose an electron. Group two, they also don't have a high ionization energy. All right. And their electron affinity isn't high that either. So they typically have a +2. Group 13 typically has a +3. Group 14 either has a +4 or a -4, depending on whether if they gain 4 electrons, it's a -4. If they lose 4 electrons, it's a +4. And that's if they form these type of bonds here, these ionic bonds here. The next one is going to be a -3. The next one is a -2. The next one is going to be a -1. That's the halogens. And the last one is a 0. And so those are some of the things that we wanted to show with this. The oxidation number for transition metals also varies. So their oxidation number, OX number varies too. So just like their number of valence electrons, it's going to vary. And again, why this is because
Micah McIntyre to the front office.
Group one tends to give that 1 valence electron away. And since it gives it away, it gets a +1 charge. Group two typically gives those 2 valence electrons away. So it gets a +2 charge. Group 17 or 7A typically gains an electron, so it gets a -1 charge. So again, this is the oxidation number right here. All right. All right, so atoms that lose electrons typically have a low ionization energy and a low electron affinity, right? They do not require a lot of energy to take an electron away, and they do not readily accept electrons. Again, in this, if you look back over here, you look at theirs, like they really don't want one. You have to force them, give them energy. You have to add a whole lot of energy. These will take one, but these will definitely, you have to force. And again, so that's what we're trying to say right here. Draw orbital diagrams of the highest occupied energy level for each of the following elements. All right. So we're going to do that real quick right here. All right. And we're going to draw these orbital diagrams. We're going to do it for lithium. And it's for its highest energy level. Okay. For its highest energy level here, if we get to this here. All right, so for lithium, if we remember, lithium has 3 valence electrons, right? And so we could do lithium. We could draw He. Okay, that means I don't even have to do that really that much. But it's going to be, here is the orbital diagram. It's 2s. It's got 1 electron in it. And then our 2 p's are all going to be empty. And it said only do this is the second energy level. So all these energy levels are empty. All right. And so if it gives us 1 electron away, it will have that noble gas configuration, which is a lower energy state for it. And it would prefer to do that. And so that's why it's going to kind of do that. All right, let's do our second one. All right. And again, pause the video while we do magnesium. Okay. Do magnesium. All right. So we're back again. We're looking at magnesium. All right. And so magnesium has two more electrons in that third energy level. Um, and so we are like, magnesium is going to oftentimes give up those two electrons and get that neon noble gas configuration. Again, they're all trying to give that up. That's why they get this positive two charge. That's why magnesium right here gets a positive two charge because it gives those last two electrons up. All right, we're going to do one more. All right, the last one, and it is aluminum. Pause the video and do aluminum. Okay, I'm back. All right, and so here is the last ones here, aluminum. If you look at aluminum, here's aluminum right here. It's neon. It's got two electrons in its S and one in its 3p. But aluminum is typically going to give up those three, and so that gives aluminum positive three charge, and that will give it an Ne. And this is a aluminum cation. This is a magnesium cation. Once it gives up those two electrons, it's got a positive two charge, and it's got the noble gas configuration. This is lower energy for magnesium. And so atoms are going to want to do these lower energy states. All right. So let's go back over here. All right. The transition elements. All right. They form cations with different oxidation states. That's what I was just telling you. Depends on what the trio is. Titanium. All right, titanium can lose two electrons and form a positive two, or it can lose all four electrons. If you look at their electron configuration, it's 4s2, 3d2. And so it could either be a positive two or positive four. Sometimes they will rearrange to have pseudo noble gas configurations, full outer shell, but not really. Copper usually has its electrons fully arranged to form C4s1 3d10 instead of 4s2 3d9. Again, this is what we were talking about with this right here. We were talking about how the transition metals right here, their number of valence electrons varies, and so does their oxidation number. It also varies. Okay. All right. Next thing here, formation of anions. All right. Anions are going to have gain. They're going to gain electrons, and it's because they have a high ionization energy. And these elements the elements that do this have a high ionization energy that require a ton of energy to take an electron away, but they also have a high electron affinity. They're ready to get them. And recognize all these right here are all nonmetals. The nonmetals typically form the anions. All right. And it says draw the orbital notation of the highest occupied energy level for each of the following things here. So we're going to do that right now. So I want you to pause the video right here. All right, and so I'm back right here. So we're going to look at fluorine. Fluorine, here is fluorine by itself when it starts off right here. We have fluorine. This is its highest energy level, 2s and 2p. And it's got all of them filled except that last orbital. It's not full. All right. But if fluorine gains an electron, it now has the same orbital notation as neon. Or I could still write it as this with the two arrows and stuff, and that's a -1 charge. What I'm going to have you do right now is I'm going to have you pause the video again, and I want you to do sulfur and bromine, okay? All right, so we're back, and so here are those electron orbital notations. And if you look, again, sulfur was short, but then it gained two electrons right here. That gives it a -2 charge, and that gives us argon's configuration. Again, this is why atoms, again, they want that noble gas configuration, which makes it stable, low energy. That's, again, stable does mean low energy, all right? And again, that's what we have right here, krypton. All right, and then the bromine has now the krypton the krypton orbital notation. All right. All right, so it says write the oxidation states for the following elements. Okay, so magnesium would be +2. Calcium would be +2. Potassium would be +1, and chlorine would be +1. And so that's what we have. Let's make sure we write that down real quick. +2, and that would be superscript. This would be +2. This would be +1, and this would be -1. You say, well, how did I come up with those numbers? I got those, the oxidation from the oxidation numbers. Those are the most common form ions formed by these elements here. And so magnesium and calcium, both are +2. And chlorine is going to be -1. Okay. All right. Next slide here. Ionic bonds, they're held together by the electrostatic force or Coulombic attraction here. Electrostatic force, attraction between oppositely and negatively charged particles. Coulomb's law quantifies the amount of force between charged particles or objects. That helps us determine the strength of attraction between ions in an ionic compound. It says represent the valence electrons in structures of compounds and molecules. Draw the electron dot molecule diagram for each of the following elements. And so we're going to do that right here. And the way you do that is all right, is we're going to write Mg. And the way we do a dot diagram is you'll do Mg, you write that, and then you write how many valence electrons it has. It has 2 valence electrons, so I'm going to do 2 dots. The electrons that are not valence electrons are called core electrons. And so we're not going to focus on the core electrons. We're just doing the valence because they're the ones that are most involved in chemical reactions. Oxygen has 6 valence electrons. So I do O with 6 dots. Okay. Sodium is in group 1. It has 1 valence electron. Okay. And so those are the dot diagrams for each of these elements. Now, what we're going to do is we're going to do the Lewis dot diagram for ionic compounds. All right. The Lewis dot diagram for ionic compounds. The first one is going to be for magnesium fluoride. And what I want to do with each of these here, it says I want to do the before and after. Okay, and for every one of these, I'm going to do the before and after. So magnesium fluoride. So magnesium fluoride. Okay, magnesium fluoride is a compound, and so we're going to do the before. The magnesium fluoride is going to be MgF2. And I'm going to tell you how we know that just a little bit later, but not right now. So before, we're going to do magnesium with 2 valence electrons. So 1, 2, and it doesn't matter where you place them. Fluorine has 7 valence electrons. 7. And I'm going to do 2 fluorine atoms. We're about done for the day here. I'm not going to do all the notes. All right. And then what you're going to have is the after. Okay. And so what happens is that this magnesium, remember, has that low electronegative affinity and a low ionization energy. So it's going to give one of its electrons to fluorine, who has a high electron negativity and a high electron affinity. And it's going to give another one to the other fluorine. And it's going to make magnesium now has a +2 charge. And each of the fluorines will be having a -1 charge. They're going to be on opposite sides of each other. A -1 charge. And this is the after. So this is before, and this is the after. Okay. All right. And this is an ionic compound. And the way this happens is that magnesium gives an electron to both fluorine atoms, making them have a -1 charge. And magnesium's got a +2 charge. Let's do another one. All right. We are going to do sodium chloride before. All right. Sodium is in group 1 Na, 1 dot. Chlorine is in group 7, and it's got 7 dots. Okay, so before and after, chlorine, as sodium is going to give chlorine an electron. This is the before. And in the after, sodium is going to have a positive charge, and chlorine is going to be a negative charge, and it's got those 8 valence electrons. All right, and so those opposite charges attract. And sodium chloride is commonly known as what? Table salt, yes. So this is table salt. All right, last one, calcium oxide. Okay, so we do the before. Calcium, it's got 2 valence electrons. And how do I know that? I look at this table. And then oxygen has got 6 valence electrons. All right. Calcium will give those 2 electrons to oxygen, making oxygen have a -2 charge and calcium have a +2 charge. And I will put the dots around oxygen. And those opposite charges attract. That's, again, a Coulombic attraction because they're oppositely charged particles. This is how ionic compounds work. One has a low electronegativity, it has a low electronegativity, ionization energy, and low electron affinity. The other one has a high desire for those electrons, a high ionization energy, a high electron affinity, and they transfer these electrons. This is called an ionic compound. Again, so this first one was called calcium, or this last one was called calcium oxide, and this last one was called sodium chloride. And you might ask you, how did you know the formulas will work? About to get that to next week. NaCl, CaO. Okay. All right. And so your homework tonight is to do this sheet. You're going to do 6 compounds. And those 6 compounds, you're going to do the before and after. So MgCl2, that's MgS, that's magnesium and sulfur. Kf, K2O, AlF3, and NaCl. And so you're going to do the before. All right. And then you'll do the after for each of those. All right. So before and after. And one thing, if you recognize that one of the characteristics of all ionic compounds, it's always between a metal and a non-metal. And so that's a characteristic that you should recognize. All right. So do this homework. It's, again, this homework is just like what we just did right here on this this stuff right here. Okay. All right. I did not get to some things over here. We'll do that on our next video. But I did not get to here it is. I did not get to the properties of ionic compounds. I didn't get to that, but I covered everything else here. All right, and so with that said, let me stop the video and again finish that up, and that's all you have to do.